Hello, welcome to our computer science lesson. Today we're going to start a new topic, which is chapter 4, and we're going to be talking about the logic gates. And this will be our last chapter in our syllabus. We have covered all the topics in the syllabus, and the rest I think will be just running on revision. So we'll talk about the logic gates. We'll see how they look like. And don't forget, when you're preparing, our syllabus number is 0478, which is computer science. Okay, let's go to the next slide. We're going to be looking at the objective. Let's start looking at the learning objectives. The first objective is to understand and be able to define the functions of the AND get, OR get, NOT get, NAND get, NOR get, and the XOR gets. So we're going to be looking at these gets here. These are actually the logic circuits, so we're going to be talking about them. And in your final examination, usually logic gates, they take 8 points. They have got 8 marks in your paper 1 examination. The other objective is to understand the binary output produced by the logic gates when two inputs are given. Then another objective, be able to produce a truth table from a logic gate, and be able to determine a logic gate from the truth table, and be able to produce a logic circuit to solve a given problem. And the last objective is being able to produce a logic circuit from a given logic statement. So some of these objectives, we'll check on them when we finish the syllabus. Sort of when we finish the chapter 4, that will be good enough to give us a feedback if whether we have managed to get on with our objectives. So we're going to move on now to the next slide. And we're going to start with the definition. What exactly are logic gates? So a logic gate is a basic foundation of a digital circuit that controls the flow of electronic signals. Okay, if you look at the history of computers, the evolution of computers, the last slide I sent you, or the last video I sent you, the scientists, they moved from those big machines, from the valves, they moved on to the transistor. From the transistor, they created what we call the circuit. That circuit, the integrated circuit they created, is the very same circuit we're talking about today. So inside that circuit, we've got the flow of the electronic signals. They run within an integrated circuit. So data and instructions are both stored and transmitted by digital computers as the binary digits, zeros and ones. So looking at the first chapter we did about the binary numbering system, we said computers, they don't understand anything. They don't understand any words from A to Z. They don't understand any symbols, but they only understand zeros and ones, which are binary numbers. So looking give an example. For example, give an example of a guy here who's sitting on his computer, and he wants to send information to the other guy here who's sitting on the other computer here. Okay, so what happens, he's going to write on his computer, on his keyboard, using the input device. The keyboard is going to write, for example, hello. That information is called analogic data. So what is going to happen, the computer, it will receive that information, but it doesn't understand these words here. We said computers, they don't understand any letters, any numbers, or any digits. It only understands zeros and ones. So it's going to take this information, which is analog data. This is what we call analog data. We said analog data is anything, any sound waves, any written text. This is part of analog. So this analog data is going to enter inside the computer, and the computer is going to convert this to digital format. So when you talk about digital format, we're talking about zeros and ones. This is what we call the digital format. So the computer is going to convert, and now is now understanding this text here in form of zeros and ones, which are called the bits or bytes. Especially each letter is called a byte, which is a composition of 8 bits. Okay, that information is going to be transmitted over the network and is going to reach to the other side. The other computer is going to understand the information because it's still in what? In digital form, which is zeros and ones. But then it cannot take that information to the user. The user won't understand the series of zeros and ones which are going to be given out by the computer. So what does it do? The computer converts that digital signal to analog so that this guy here on the other end, he can read the information which is hello. So this is how information is transmitted, and this is what this statement is saying. Data and instructions are both stored and transmitted by the digital computers as binary ones and zeros. So if he decides to store this very information, it's going to be stored like zeros and ones. Only the computer translates to analog data when the user wants to make a reference to the information. So various tasks are performed in a computer by switching a high voltage or a low voltage through a digital circuit called a logic gate. So when we talked about the third generation in the evolution of computers, we talked about the integrated circuit. Then on the fourth generation, they moved into the integrated circuit at large scale, which was the processor. It means that the size of the integrated circuit was now very small, but the number of signals inside it, they added more signals to be transmitted inside that small integrated circuit at large scale. So high voltage is represented by a 1 and low voltage is represented by a 0. Or in other words, it's represented, 1 is represented as on and 0 is represented as off. This is what will be happening inside the computer. So there are only two values which can be taken by input or output, which are 1 and a 0, or which is an on and an off. So it depends now with the language each technician or each programmer will be using. Some they use what we call high voltage and low voltage. Some they use ones and zeros. Some they use true or false. So these three statements. So we have the other one which is true. So which is on, it's true. Off, it will be false. So these are the three statements which are basically used. Some they use high voltage. So I have to abbreviate here. Writing with the mouse is a little bit difficult. Okay, high voltage, and here it will be low voltage. So these are the three languages or the three terms which can be used when you're talking about logic gates. So don't get confused. When you hear somebody saying high voltage, it means we're talking about an on, or we are talking about true, or we're talking about a 0. Sorry. This one will be a 1 and this one will be a 0. On, a 1. Off, it's a 0. True, it's on or it's a 1. False, it will be an off or it will be a 0. So this is the language which will be used over and over again. So depending with the programmer or the IT. Okay, so we also have these three sets of interchangeable. So these three sets are interchangeable. These three sets. So we're actually talking about the high voltage, we're talking about the on, and we're talking about the true and false. So they are interchangeable, and it depends with the user which one will be using. So it'll be basic. So looking at the three sets of the logic gates we talked about, of the interchangeable states, like the on and off, the true and false, and the high and low, it means that high voltage is represented by binary digits. And this means that some of the circuits, they only have few logic gates. We're talking about the integrated circuits. And some of the integrated circuits, they have more. So which ones have the less and which ones have the most? So let's go back to our evolution, the evolution of computers. In the third generation, they created what we call the integrated circuit. That year, or those 4 years, were actually about the integrated circuit. So we're actually talking about circuits which only have a few logic gates. Then from the fourth generation now, they created what we call the integrated circuit at large scale integration. So it means that we are actually talking about the microprocessor. That microprocessor we're talking about, it had thousands, or it has thousands of logic gates which are integrated inside that device. What was the objective there? To increase the speed of the computer and to reduce the size of the computer. So now computers, they have thousands if not millions of logic gates which are inside there, which help to control the flow of electronic signals in a predefined way or predetermined way. So this was why I gave you that slide or the video on the history of computers. I had forgot about that, but let's just integrate that previous lesson on the evolution with this one of logic gates and the von Neumann architecture. Okay, so we defined the logic gate, what it is. Then we had some of the key terms like the digital circuit. A digital circuit is where electronic signals are one or two values, which is high or low. Then we also defined the voltage, the potential difference across an electronic component needed to make electricity flow through it. Then we also talked about the microprocessor, which is an integrated circuit that provides the same functions of a CPU. Then we're going to be talking about a truth table. What is the function of a truth table, or what it is? What is it? Sorry. A way of showing every outcome of a logic gate. So we want to get the results of the logic gates, then we have to use what we call the truth table. So let's move on to the next slide. We've got the types of logic gates. First, we've got the AND gates, the OR gates, the XOR gates, and the NOT gates. So we shall be working with these gates, and we're going to describe each of the logic gates. Then as we go on with our lesson, we're going to make a combination. It might be these two, or it may be a combination of three of these, or it may be a straight combination of the 4 gates to create one electronic circuit. So we're going to be looking at that in our lessons. Okay, let's start with the first one, which is the NOT gate. The NOT gate is represented by this symbol. We draw a triangle in the form like this. You put a line and you put a 0 there, then you put another straight line. So this means that it's a NOT gate. A NOT gate, it has got input. Data enters through, or it flows, the signals, electronic signals, they flow through this point and they go out through this point. So this can be represented as A, and this can be represented as X. Okay, if you look at the NOT gate, it has a single input, which means that if you see one line here, it means it's a single input. This is a NOT gate. It has got a single input, and it also has a single output. So if you see one other line at the end here, it means it's the output, which will be a single output. So when using a logic gate, there is only one input and one output. The output will be X. So X will be our result, which is a high voltage or a low voltage. If the input is low voltage, this means that X will be only 1 or a 0. So as a logic statement, we can represent that, or before we talk about the representation, it means that if you input a 1 here, which is on, what will be our result here? It will be a 0. If you input a 0 here, what will be our output? It will be a 1. So this is what happens with a NOT gate. If it is not a 1, what will we get? A 0. If it is not a 0, not, what will we get? A 1. So it has got one input, but always that input, if it is positive, is going to give us a negative result. If it is a negative result, it's going to give us a positive result. So we can represent this in a statement. I'll write up the statement below here. So it means X is our result. So we have X is equals to not, which is our get, A which is our input. Okay, or we can represent it, we can represent it as X is equals to A. Sorry for my English, I've been speaking a lot of Portuguese for long, but I think I'll keep up. Okay, so we can also represent it as a logical statement like this. Okay, let's go now to the truth table. On the truth table now we need to see the results, the function of a truth table, or like we said in a definition of a truth table is a way of showing every outcome of a logic gate. We need to see the outcome. Let's go back here. The outcome, if you input a 1, what comes out? So we have to make out a what we call a truth table. So if you look here, we've got input, which is our A, and output, which is our X. So if you input a 0 or a false value, you're going to get a true value here. An off value, you're going to have an on value. A low value, you're going to get a high value. If you, or otherwise, because we've got two options. If you input a 1, you're going to get a 0. Either you're going to get this a high value, you're going to get a low value, or if you want to say if you put a true value, you're going to get a false value. So this is what we call a truth table. It shows us a way, it shows us every outcome of our logic gate. So it only works with two values, either a 0 or a 1. These are what we call the binary numbers. Okay, let's move on to the next gate, which is the AND gate. The next one is the AND gate.